Hi all, I welcome you all to the next lecture today. Today, I'm going to start your fourth unit, and fourth unit topic is space exploration. And the first topic of it is introduction to the rocketry and its type. Prior to this, we have covered introduction about the air breathing engines, and where you have been given a detailed exposure about various kind of engines used on the aircraft, their relative advantages and disadvantages, their functioning, and it all. So, from that, you already know those are all air breathing engines, right? The engine which requires oxygens, right, from the outside environment for its combustion, which is known as air breathing engines. So they are having their own limitations, right? They cannot be able to fly at very high altitude, so altitude limitation is there. But at the normal operating range, right, as per the international standard atmosphere, right, up to an altitude of 25 kilometers, they are having very good performance. All right, so we can use those air breathing engines based on the gas turbine technology. Today, in this lecture, you will be given a detailed exposure about the principle of rockets and various kind of rockets available for space exploration. All right, so let's start our journey of the rocketry here. So first question comes in mind. What is a propulsion? So propulsion, by the name itself, is a force which basically required to propel any object into the air, right, into the air or into the surrounding. So it is nothing but is act of changing the motion of a body. So it may be translation, it may be rotational as well. So translation, it can produce linear motion, right, and may be moving at slower rate or maybe at faster rate, right. It can also create a rotational kind of motion that is called turning about an axis. Usually in our automotive vehicles, right, we find that kind of motion that is also called propulsion. So basically, propulsion being divided into two, right? One is called space propulsion, another is called jet propulsion. And jet propulsion, we have clearly seen that in jet propulsion, the engine which works on this is known as air breathing engines, right? And space propulsion particularly required for doing the space exploration, all right? And for in when we are going in space, all right, in space, as per the international standard atmosphere, we know that as we go high, density reduces, and when we are talking about space, outer space, where complete vacuum may also be possible, in that case air breathing engines will not be sufficient enough, right, to be operate. So we do require some new kind of engines for this purpose. For that reason, the rockets were designed, and we are using those particularly for space propulsion activities. So rocket launches, right, launches controlling satellite motions and maneuvering spacecrafts. For that purpose, we use these space propulsion devices. And jet propulsion, particularly, we're talking about how actually do they work. They work by using the momentum of ejected mass to create a reaction force or inducing the motion. There was a time, right, in early 90s. It was a belief that rockets could not work in vacuum, but no, that concept was wrong. They can operate in vacuum because they do not interact with the outer atmosphere, right, for any kind of its functioning, right. That's why we do say, right, rockets are non-air breathing engines. So jet propulsion, if we classify it in detail, we can say the first system that we talked about jet propulsion is nothing but air breathing systems, right? They are also called as duct propulsion. So vehicle carries its own its own fuel, and the surrounding air particularly is used to get utilized for combustion and thrust generated. So gas turbine engines, right, used on the aircrafts are the example of the air breathing system. And second one is rocket propulsion, right? This is one of the example, right? Particularly using the jet engine based engine on its operation. This is a car, right? Experimental car that has utilized the jet engine. The rocket propulsion vehicle carries on fuel and oxidizer or other expelled propellant to generate thrust, right? So can operate outside of the Earth atmosphere because it doesn't interact with the atmospheric outer atmosphere, right, for its operation. So there is no limitation of altitude, right, for the operation of rocket, while it was a limitation on the air breathing engines. So they find applications, right, in launch vehicles, upper stages, Earth orbit satellites, and interplanetary spacecraft. So this is one of the example, right? A rocket powered scooter, right? So this is one of the example. So the principle on which basically rocket works is nothing but Newton's third law of motion. So every action there is an equal and opposite reaction, right? So high jet of hot gases getting expelled through the nozzle, and as a result of that, we do get the thrust. That's a basic fundamental principle of rocket propulsion. So we compare between air breathing and non-air breathing engines. We can compare in this way, right? In air breathing engines, altitude is limited because the combustion within the combustion chamber of air breathing engine depends on the local atmospheric air properties, right? As we are going at very high altitude, we may not be able to get sufficient amount of air inside, and because of that, performance of engine will be deteriorating. And that is, if that is the case, in that case, the sustainable flight may not be possible. That is another big issue with the air breathing engines. And if we talk about the non-air breathing engine, where engines are not going to interact with the outer atmosphere, so there's no altitude limitation. So space travel is possible only with the help of non-air breathing engines. Second point, thrust decreases with altitude because our engine is basically interacting with the outer atmosphere. So as the parameters, right, that's called mass flow rate, which is entering into the engine, is getting decreased, because of that thrust will also decrease. But in the case of non-breathing engine, right, this is opposite. Thrust increases or improves slightly with the altitude, because as altitude increases, temperature decreases. So we'll have a better cooling, right, around the combustion chamber. So we can even go for generating large temperature within the combustion chamber, which can be expelled through the nozzle to generate enhanced thrust, right, at a higher altitude. So there's a second point: the thrust increases or improves slightly with the altitude. And third point, when we're talking about the flight speed is always less than the jet speed. So in the case of air with the engine, the speed by which your hot gases are expelling through the nozzle, right, but the reaction which we are getting out of it will be lesser. So speed of the vehicle is lesser than the jet speed. But in the case of rocket engines, right, flight speed is not limited, can be greater than the jet speed. The last point, high efficiency and reasonable flight duration is possible only with the air breathing engines. Sustainable flight for longer range is possible, but here in non-air breathing engine, it is having slightly lower efficiency, right, and extremely high flight speed, and particularly they do use for small duration, right, because the combustion, right, process will be what we say, operation is something called intermittent type, right, in the case of rocket engine. But in the case of air breathing engines, right, is a continuous operation. So that's why reasonable flight duration is possible with the air breathing engines, but here it's not, right. So short period of time we do use the rockets, right, particularly for launching the spacecraft right into the outer space. So these are the broadly differences between the air breathing engines and non-air breathing engines. So if we look at the applications, right, as I said, right, these rockets do space propulsion devices do find application in launch vehicles, right. You look at this, for launching the spacecraft, right, from the earth, we do need a booster, right. The booster stays than carrying the launcher, right. So for launching device, do we use we basically use the rocket, right. And then ballistic missiles. So this is one of the wonderful example of space propulsion device or rocket, right. Like our in India Agni series, right. You can take inter continent ballistic missiles. Those all ballistic missiles do work on the principle of the non-air breathing engines. The Earth satellites, right? This is another example of a space propulsion device, right? And upper stages, particularly when they are getting expelled into the low Earth orbit, there also we use the space propulsion devices. And interplanetary spacecraft, right? and manned space flight, right? This is another example of space propulsion, all right, devices. So if we look at the functioning, right, space propulsion functions, the primary function of space propulsion is to launch and descent, right, launch and ascent the spacecraft, then maneuvering where maneuvering is required, orbit transfer from one orbit to another orbit, station keeping and trajectory correction. If it is going to be deviating from its planned flight path, then it should be corrected with the help of small propulsion, a small space propulsion device. Auxiliary propulsion particularly required for attitude control, reaction control, and momentum management. For that purpose, basically space propulsion devices are being used. Right, those will be called magnetic plasma rocket, or maybe nuclear rockets can also be used. So this is one of the photographic images, right? When your spacecraft is traveling from one orbit to the another orbit with the help of space propulsion device. If we look at the brief history of rocketry, particularly, so when we talk about space exploration, right, this is a fantastic, science of, science of astronomy, right? So space exploration is a ongoing discovery and exploration of celestial structures, right, in the outer space through the continuous searching and utilizing the space technology. Studying about the space is carried out by the astronomers, right, with the telescopes, mainly, and physical space exploration of the space is conducted by both unmanned robotic probes or human space flights. Right, USA has done a lot of work, particularly on human space flight. So, common purpose of exploring space, including advancing scientific research, national prestige, uniting different nations, right, ensuring the future survival of humanity, and developing military and strategic advantages against other countries, right. So already we know that we look at the history, right, particularly how actually these things have started, right. Human have dreamed about the space flight since antiquity, right. Indians and Chinese, they do use the rockets for commercial and military purposes centuries ago, but only in the later half of the 20th centuries were rockets developed, and that were powerful enough to overcome the force of gravity to reach orbital velocities that could open space to human exploration. So the earliest, right, if we look at the early times of 300 BC, right, this was the time when rockets basically were used for ceremonial or military purposes, right. So they do use the black powder, right. This is one of the historical picture, right, taken from the Chinese website. Actually, I have taken that. So this is the one who tried to launch himself to the moon by attaching 47 black powder rockets to a large wicker chair, right. This is a chair where 47 these black powder rockets were attached, and with the help of that he tried to launch himself into the outer space, but he could not succeed in that. All right. So later on, Russia, right, particularly Russia, they have done uh, basically a tremendous amount of work, right, in early time, right, in early 90s. This is the Professor Konstantin Tsiolkovsky, right. He spent a lot of most of his own life in developing the orbital mechanics and rocket equations. So basically, he has given a lot of ideas about how to design the rocket, and how to launch the rocket. All right. So earliest practical work on rocket engines, basically that will be that now we are utilizing those are done in early 20th century. And if we look at the development framework, right, early development work framework for space exploration that was done in basically three countries, right. The first significant contribution was made by the Russia, right, by Professor Tsiolkovsky, right. Then followed by the United States, right, where Robert Goddard, right. So if you look at the United States, right, this is the professor, another professor, Dr. Goddard, right. he also contributed a lot, right? Particularly, so he devised and proposed the first liquid fueled rocket in 1926, right? 1926, and the third contributor, right, basically was Germany, right? This is the famous, scientist, Dr. Von Braun, right? He has basically he is known for developing the V2 bomber, right? Herman Oberth also contributed in that significant discovery of German V2 bomber. So if we look at the brief contribution, right? Nazis, right? Basically, Germany has shocked the world by displaying the B2 bomber in the World War II. And that was the turning point, and people started about thinking that there's a possibility that we can develop an engine which can definitely make us to do exploration into the space. So in the 1930s and 1940s, Nazi Germany saw the possibility of using long distance rockets as weapon. Late in World War II, London was attacked by 200-mile range B2 missile, which basically flown 60 miles high over the English Channel at more than 3,500 miles per hour speed. That was the speed of the V2 bomber. And after World War II, the United States and Soviet Union created their own missile programs. Right on October 4th, 1957, the Soviets launched the first artificial satellite called Sputnik 1 into the space, and that was the turning point of starting of the space program. And immediately after that, it was followed by the US, and US have done a series of satellite launching as well as human space flights. So 4 years later, on April 12, 1961, Russian Lieutenant Yuri Gagarin became the first human to orbit Earth in Vostok 1. So his flight lasted 108 minutes, and Gagarin reached an altitude of 327 kilometers. All right, so this was the time, right? Basically, early formatted year, but it has made a biggest contribution. It has made a biggest contribution, particularly in the developing of future rocketry. So these are the three, biggest contributors, right, in the early stage of developing the rocketries, right, which has made now us comfortable to do the space exploration. So space propulsion system classification, particularly we look at, we can classify them as stored gas, right? That is called a gas is stored at particular pressure, and then we are expanding it and we are getting the reaction. By that way, you can do, or with the help of chemical, propulsion, you can execute the space propulsion. Or there are two more category: electrical and advanced propulsion. Electric, you can say electrothermal, electrostatic, and electrodynamic propulsion also possible. And basically, based on these devices, we are using in the spacecraft, particularly for doing motion from one orbit to the another orbit. For that purpose, we are using the electric propulsion. And advanced propulsion is also there: nuclear, solar, thermal, laser, or antimatter, right? Propulsion. These have also been developed, right, particularly for trajectory correction, right, altitude control purposes, right. So here we look at the chemical, propulsion. Actually, this was a biggest discovery, basically, chemical propulsion, and here a lot of work has been done, and we are now capable of producing or developing the rockets which are basically capable of sending us to up to the geosynchronous orbit. All right. So chemical propulsion basically having main categories, right? Three categories: solid, liquid, and hybrid, right? Then liquid, particularly liquid propulsion, getting divided, right, into two: monopropellant and biopropellant. These are the basic, classification of liquid rockets, right? And when we are using the liquid, right, propulsion, that means oxidizer and fuel both are in liquid form. So in order to make them mix, we do need pressure feed control and pump feed control, right, particularly to make it happen. So cost wise, right, liquid rocket motors are slightly costlier compared to the solid rocket motors, where fuel and oxygen both are in solid form. All right. So these are the broad, classifications of space propulsion system. So if we go for the first case, as I said, that the stored gas propulsion. So stored gas propulsion is nothing but where you are storing particular gas, right, at high pressure in a tank, then you are sending it through via valve and pressure regulator through a thruster to generate the thrust. So this was basically known as primary or auxiliary propulsion. So look at here schematic diagram. We are having a gas container where we are storing gas at a very high pressure. All right, so this is the pressure gauge which will tell you the initial pressure of gas by which it is coming out. So this is a high pressure isolation valve, right? Then filter will be there to remove any foreign particles out of the gas which is getting expelled through the thruster. After filter, pressure regulator is there, right, which will regulate the pressure at which pressure need to be sent to the thruster, right. Then low pressure isolation valve. Why these isolation valves? To reduce the noises, right, in the piping systems. And finally it enters into the combustor, right, thruster, and it getting expelled at very high speed, and as a result of that you are getting the reaction. So high pressure gas or propellant is fed to the low pressure nozzle, right, through pressure regulators. Through pressure regulator, release of gas through nozzle generates the thrust. So currently used for momentum management of space space telescope, right. Propellants include nitrogen, helium, nitrous oxide, and butane. Very simple in concept. So this is a very simple, propulsion system, right, called stored gas propulsion, right, and it's been used for momentum management, right, particularly on the spacecraft telescope. So if we look at the chemical propulsion classification, right, here basically liquid propellant. When we talk about liquid propellant is liquid, right, we are having two different container. One will have fuel, another will have oxidizer, and both are in the form of liquid, and now both has to be mixed, right, in the combustion chamber at appropriate fuel and oxidizer ratio. And for that purpose we do need two separate pumps, right, one pump for oxidizer, one pump for fuel, and then both are getting mixed here, right, in the combustion chamber, and finally combustion will occurs, and finally it's getting expelled through the nozzle, and we get the thrust, right. So pump feed system is needed, right, and these kind of chemical propulsion system basically we need to use in launching devices, right, launching vehicles. So larger upper stages, right, and so small and upper spacecraft also they do find application, right. So monopropellant, now only single propellant will be there, that itself will have fuel only, right, and biopropellant, fuel and oxidizer both will be stored, right, in this container. So solid propellant, second category, right, is the first category is called liquid propellant, second category is solid propellant, where fuel and oxidizer both will be mixed and they will be kept at solid form, and in the moment you start the first spark, and they will automatically start burning, and you will get the thrust. So this is second image you look at, this is called solid propellant rocket, where fuel and oxidizer are here, right. This kind of structure you are saying, but is around the periphery. This complete thing will be fuel and oxidizer. Inside this core you are seeing here, burning will take place. So with the help of igniter, you will start the burning from one point, and from this point, and they will start burning like that and go up to here. All right, and the moment your burning starts, burning may be going towards the circumference both side, right. So burning will take place like this, and the exhaust gases which are coming out through the nozzle will be expelling at high velocity, and you getting the thrust. Right, this is the example of solid propellant, right? Solid propellant rocket. But particularly, we use the solid propellant rocket for booster stage, right? Initial stage. So, launch vehicle, right? Space shuttle, spacecraft, fuel and oxidizer, and solid binder. And last one is hybrid, right? Where solid fuel and liquid oxidizer will be used, right? So, solid fuel will be in solid form, right? Within the container, and oxidizer will be in liquid form. The moment your oxidizer comes in contact with the solid fuel, your burning will start, right. Burning will start, and that is being expelled through this nozzle, right, and we get the thrust. So sounding rockets, right, basically it been used already to predict the weather phenomena. to reproduce the weather phenomena. So these are the broad classifications of chemical propulsion, devices. So if we look at the monopropellant system, right? Monopropellant system. This is a container, right, where we are basically putting only fuel. So nitrogen or helium is filled here, and outside we are keeping the hydrogen. So hydrogen is basically our fuel, and this is your gas which is filled at high pressure, right? This is called propellant tank, and followed by the pressure gauge, then isolation valve is needed, and after that filter, and then immediately after that there will be some number of thrusters through which these hot temperature gases will expel and you will get the thrust. So hydrogen is the fuel, this is the most common use, and monopropellant formula for it is N2H4. So decomposed in the thruster, right, they will go and they decompose into the thruster using catalyst to produce hot gas for thrust, right? So older system used hydrogen peroxide before the development of hydrogen catalyst, right? So they typically do operate in the blown down mode, right? So the moment hot gas is generated, they will be blown down from here and you will get the thrust. So typically operate in blown down mode, pressurant and fuel in common tank. So this is the high pressurized air, and this is the your hydrogen your fuel. So high pressure air along with fuel will come here, and with the help of catalyst, right, they will convert to the gas, and finally they will get thrust exhausted to the thruster to produce the thrust. Bipropellant system, that means it will have two propellant itself. One propellant will be called as fuel, another is called oxidizer, right? So a fuel and a oxidizer are fed into the engine through injector, and combustion in the thrust chamber will happen. So fuel here, oxidizer will be filled here, both pressure regulators are there, pressure gauges are there, isolation valves, right, and finally they come here, get mixed here, and combustion starts, and finally getting expelled. So both kind means some of the bipropellant may have hypergolic propellant. The moment they are coming into contact, right, they will react and combustion occur. So that means no separate igniter is needed in the case of hypergolic propellant. So hypergolic, no igniter needed, propellants react on contact in engine, right? Cryogenics propellants include LOX and lithium hydrogen, right, LH2, right? LOX basically they may, you look at the temperature, right? Cryogenic propellants are those which are basically react at very low temperature. So temperature varies, you can see all the minus, right? So here basically igniter is required to ignite them, and final combustion will happen. Storable propellants include kerosene, right? RP1, hydrogen, nitrogen tetroxide, right? And monomethyl hydrazine, right? These are the commonly used, right, right? And LOX can be used as oxidizer, right? Here, and both will be in a liquid form. Both will be in liquid form in the case of bipropellant. What are the advantages and disadvantages? Right, can be reused after recovery. This is the one biggest advantage of liquid propellant. They are flexible and greater control over thrust. But in the case of solid propellant, the moment you started the combustion, you cannot control the combustion. But here you can control the combustion with the help of intermediate valves, right? You can control the rate of burning, right? So they are having greater control over the thrust. It is much easier to terminate the operation in midway. In the case of an emergency, you can all of a sudden switch off the combustion, right? More economical for long range space and military operations. More complicated, right? Problems arise due to valve leakage and vibration. This is the disadvantage, the biggest disadvantage of this system. Complicated structure compared to the solid rockets, right? Here a lot of valves and isolation valves are needed, right? So low leakage problems may be there, and vibration issues is big in the case of liquid rocket motors. So much longer time to design and construction, right? They do require large time, right? Much time for design and manufacturing. Not properly shaped because of propellants are poisonous and corrosive. So we cannot do too much aerodynamic shape to the liquid rocket motors. This is the disadvantage. So biggest disadvantage basically we need a feed pump system. And for operating the feed pump system, we need a pump, right? And those pump need to be require, right, input power. And for that purpose, we basically do use the combination of turbine and compressor kind of pump. So propellant delivered to the engine using turbo pump, the gas turbine derived centrifugal or axial pump, large high thrust and long run system, right? Basically these engines are being used. These are the two examples, right? H1 engine turbo pump, and this is F1 engine turbo pump. So this is just similar like gas turbine. So this is the additional weight penalty to the rocket, and they do need some work input, and that is another overall efficiency effectiveness of rocket may be slightly lower, right, compared to the traditional rocket. So F1 engine turbo pump, if you look at the turbine drive, there's 55,000 brake horsepower, right? So these are all, propellant. These are type of propellant, kerosene, right, which has been given. The kerosene is your fuel, and LOX is your oxidizer, right? Basically used on chemical rocket. So this is the disadvantage, that we require the few feed pump systems, right? And because of that, it is increasing the design very complicated, as well as vibration and leakage issues will be more. So for today, this much is enough. So here I'm closing my discussion, right? So as a summary, I must say today I gave you some introduction about the rocketry, right, and classification of space propulsion devices. How many types of rockets are there? Solid, liquid, right? Rockets and hybrid rockets. Introduction have been given to you, and we have seen a detailed, explanation about the solid propellant rocket as well as liquid propellant rockets, right? Where you have been given a proper idea, right, how fuel and oxidizer are being stored and how they are going to react, right? In the case of solid propellant rockets, right, we do need a igniter to start the ignition, but problem with the solid propellant rocket is we cannot control the combustion. Once your combustion has start, right, we cannot stop it. So rate of burning also we do not have any control, right? The way they will burn, they can go the direction in which they will burn, they can go, right, because we don't have any control. All right, but direction at least we can control, but burning rate we cannot control over it. So in the case of emergency, all right, we cannot stop the operation of solid propellant rocket. But in the case of liquid propellant rocket, as we are using the feed pump system, so the moment if we find that there is a problem, there is an emergency, we can shut down the operation of the rocket. And they one another advantage of liquid propellant rocket is they are reusable, right? Once they have used, right, then again we can reuse the components of liquid propellant rockets, right, for its operation by filling the fuel and oxidizer. But in the case of solid propellant rocket, again you have to redesign the entire casing in which you are going to store the propellants, right? So but geometry wise, if you look at liquid propellant rockets, manufacturing is very complex because a lot of other subcomponents are needed. But solid propellant rockets, right, their design is very simple. So in a shorter period of time you can manufacture large number of solid propellant rockets compared to the liquid propellant rockets. So that's why launching a vehicle, solid propellant rockets do find in first stage, right, that in the booster stage, right, the moment your rocket is getting lift up from the ground, for that booster stage we use the solid propellant rocket, because solid propellant rocket generate the larger thrust, right, compared to the liquid propellant rocket. So in that case we do use the solid propellant rocket, right, then followed by the liquid propellant rocket. You also have been given idea about hypergolic propellants. Or hypergolic propellant, the moment they comes into the contact, automatically burning starts, right? That means they do not require any kind of additional igniter for its conversion, right? And then we have seen the monopropellant and bipropellant kind of system, right, in the liquid propellant rocket, that also been covered in detail, right? And you have also seen the pressure feed, stored gas propulsion system, where high pressurized, gas is getting stored and finally it's getting expelled through the thrust chamber, and we are getting the thrust. This is a very simple type of propulsion system. So these all things basically we have covered today, right? And you have given a brief history of rocketry and space exploration. So if you are having any doubt in this topic, particularly what we have covered today, feel free to write in the comment section. Right, I hope you might have like the content of this video. Please do share and like and subscribe to my channel. So see you all in the next class with a new video with the remaining portion where you will be exposed to the solid propellant rockets in detail. Right, then we'll go to the hybrid rocket motor, how to design and what are the advantages of hybrid rocket motor over the traditional solid propellant rocket. Alright, and finally we'll go for some performance parameters of rocketry. So thanks for listening to today's lecture. See you all in the next class. Have a nice day. Good day.